All right. Hello, everybody. Welcome to the brand new online version of CSC 484/584. This is still building game artificial intelligence. I'm still Chris Martens. Things are just a little bit different now. So today we're going to get into, after a 2-week hiatus from previous material. Luckily today we're kind of starting fresh and beginning with a new topic. This is going to be procedural content generation, frequently abbreviated PCG in the games industry. And this lecture is basically just going to introduce an overview what PCG is and start getting into a few of the simpler techniques for starting to use it in your games. So just a couple of announcements before we get into the lecture material. Obviously, we are moving this course online, and that's a pretty significant change. I did try to cover as much as I could about all aspects of the course in that information document that I posted to Piazza. I strongly recommend you review it in detail. Hopefully it contains information, it contains the answers to most of the questions you would have. I'm just going to summarize kind of the high level, kind of higher order bits that you really need to know in these next couple slides, but definitely refer to that document for the full set of policy changes. So the lecture videos are going to be posted no later than 6 p.m. on Tuesdays and Thursdays, which is our regular class time. That's Eastern time. In order to kind of make sure that folks are watching the lecture videos on a regular schedule and not getting too behind, I am going to try to post a quiz for every single lecture. But don't think of this as like more, high stakes tests. Like these are, these quizzes are really just for your benefit and to try to keep you on a schedule. And so to try to, in that spirit, to be in that spirit, I'm leaving the quizzes open for 1 week, and I'm going to make it so that you can retake it however many times you want. So clearly, if you got the time, you can take the quiz multiple times and see what the correct answers are, and then go back and fill in the correct answers. That's perfectly fine and expected. The goal is just to get you to reflect on the lecture material after you view it. So for example, I'm going to post a quiz for today's lecture, and that's going to be open until 1 week from what would be the end of class time, so 7:15 p.m. on Tuesday, March 31st. So there have been some pretty big changes to the project structure for 582. We previously had the last two lecture periods reserved for presentations for 582 students. And instead, so instead you'll be posting lecture videos. That's actually not what this slide is about. Sorry, presentation videos that'll be reviewed by the undergraduates. That's I think, did I talk about that on the next slide? Yeah, that's the next slide. Got ahead of myself. So you did have a milestone that was originally due this week. Was going to be the project update, which originally was supposed to be kind of you should be almost done by now, so please do your first draft of your final report, and we'll give you some early feedback on that. In order to give you a little bit more time to get to that point, I am instead asking for a much lighter weight project update. So there's just a few questions, open-ended questions, that I'm asking you to fill out a form just to kind of keep me informed of where you are on your project. Just only one member of each team needs to fill it out. Please do so by Thursday. It should not take you very long. That is just so, basically to hold you accountable and make sure that you're still hopefully making some progress on your project, even if you need to kind of scale back some of your goals or change the way that you're collaborating. Now that we've moved to fully remote, you can definitely report that in your status report. So I'm going to continue having office hours at my regular time. So that's 2 to 4 p.m. tomorrow. I'm going to post a Zoom link on Piazza, and that's going to be drop-in. So I'm going to have the Zoom meeting running that whole time, and I should get a notification if anybody enters the meeting. The TAs decided that they would prefer to have appointment slots for their office hours, so they'll be posting more information about that on Piazza. Okay, what I was saying before about the project, the 582 students who are doing the project are going to create a 5 to 6 minute long video of their presentation. And I'll give you a place to upload those videos by the second to last day of class, basically, the time that you would have had to be ready to give your presentation. And then I'm going to ask the undergrad version of the course students, the 484 students, to watch probably some subset of those video presentations and submit online evaluations of the videos. Again, here's the link to the full information about moving online. Please do post to Piazza if you have any questions about the online course logistics. All right, time to get into the fun stuff. So today we're going to be talking about procedural content generation, and this term has been around for a while, but people argue about various pieces of it. And some, one of the more contentious terms is the word content, because it's like, well, okay, what exactly does content mean in the game? Isn't content just everything? And some people would say, yes, it's pretty much any aspect of a game that you could generate through some procedure or process rather than doing it by hand. And some people would say, well, there are some things that are more like kind of behavior, and that's more like any kind of game AI is sort of procedural behavior generation, but content refers to strictly those things that are kind of fixed at the start of the game usually. So we're usually talking about things like levels, world maps, mazes, dungeons, like details of the level, like things like textures and the terrain that you might see in the world. And maybe if you have like some AI characters wandering around this world, maybe some aspects of those are procedurally generated. You also hear people talk about procedural generation of quests and narratives, and some of my own research focuses on those things. That I would consider it procedural generation, but maybe not with the content word included, right? I mean, it's it's not a bright line what divides kind of content from whatever else there is, kind of dynamics or behaviors. But some of these things are certainly generated by things, like generating narratives, for example, can be done through methods more recognizable as character AI. Okay, so at this point, I am going to give you a couple of minutes to write down any examples of games you happen to know that use PCG. And think about specifically what are they generating? What kinds of content are they generating? If you don't know any, that's okay. You'll have a chance to talk to a neighbor. If you don't know whether the game you're thinking of uses it, that's okay. You can write it down and talk about it, and maybe your neighbor knows. So I'm going to take 2 minutes for you to just make a list of any that you can think of. All right. So hopefully you've had a chance to reflect a little bit on some of the games you may have played that use PCG. If you have the opportunity to talk to anybody else in the class about what you came up with, please do so. Okay, so today what we are going to cover is the history and motivation, how random numbers are generated and how that kind of fits into all of the algorithms we'll talk about, algorithms specifically about placing objects, and algorithms for generating mazes. So PCG has been around for a long time, certainly much, depending on how you kind of count, much longer even than it would appear in its kind of strictly digital form. But in digital games, you can trace a lot of these techniques back to arcade games and PC games from the 80s, such as Elite, which was a space exploration game that had generated galaxies and planets. And this whole like star fields and everything that you're flying through has like generated star placement. Exile, which procedurally generates dungeons that you can explore, and games such as Rogue and later sort of popularized by the game NetHack in 1980 and 1987 respectively, which are most well known probably for their ASCII art, kind of glitchy looking aesthetics. They sort of have this very 80s style and look to them because every component of the screen, every sort of image is just an ASCII character, or rather the extended character set, but is just a single character. So like the player is represented by an @ sign, and you sort of slowly learn to kind of decode all of these different symbols in the levels. But the relevant part of these for this class is the fact that these games are, they get harder and harder as you go down the levels of the dungeon. The idea is you're going deeper and deeper into a dungeon with some eventual goal like all the way at the bottom. And as you go, things get harder and harder. But they have this characteristic called permadeath, which means if your character ever dies, of which, and there are many ways to die in these types of games. If your character ever dies, you have to start over completely from the beginning. So when you play these games, you'll find yourself playing the early levels very often, right, repeatedly, and you don't want to, like, the game designer's goal is to have that not be a repetitive experience and not to have people basically having to play the same levels over and over again, but rather to get a slightly varied experience every time they have to start the game over, which again is very frequently. So this gave rise to a genre of games known as roguelikes, named after Rogue. And that genre kind of still persists today, the sort of idea of procedurally generated levels where difficulty increases as you go, and there's some notion of permadeath and having to restart. So for these games, like, the original motivation was to provide this kind of replayability and variation for the player, whereas for the games like Elite and Exile, actually some of the original motivation, and this is actually true for Rogue and NetHack as well, but they were actually constrained by memory resources, right? Like they didn't actually have enough memory to store all of the combinatorially many options of possible galaxies that they might want to create, or to like author a whole bunch of these by hand and then ship that with the game. So instead, they created an algorithm that would do it kind of as programmatically rather than as part of the game data. So these are sort of more process-intensive approaches to content creation rather than like data-intensive is one way of thinking about it. Yeah, so that's kind of some of the earliest examples. And then moving on to, I guess, the 21st century at least, we get into more, there was sort of a resurgence of interest in procedural content generation that was created by the game Spore, uh, spearheaded by Will Wright, who made the Sims games at EA. And this was kind of one of these games. There've been a few iterations on this theme since then, but I think this was one of the first that really had this ambitious goal of like, let's try to generate an entire universe. Let's try to make planets that you can fly between with spaceships and land on the planets and generate like life from um, kind of the early forms of life, like single cell organisms, and just evolve the whole tree of life kind of from there, and have the, you know, sort of terrain and interactions between different species and everything, and flora and fauna and all of that, like, be procedurally generated. Of course, the like main thing that people really liked, this image is stuck behind the other one. The main thing that people liked about this game was actually the creature creator, where you could set different sort of physical parameters of your evolving creature, and then that would change the way it moves through the world and the way and its like chances of surviving in the environment. In 2014, there was a sort of sequel to Elite, that 1980s game release called Elite Dangerous, which I think is mostly a kind of a visual upgrade, but a lot of the mechanics are pretty similar. And so you're, you know, flying between procedurally generated worlds in procedurally generated galaxies. And then we have this whole kind of modern era of games that are inspired by roguelikes. This is sometimes called roguelites with a T, because people think, well, they're not really roguelikes because they use, you know, higher fidelity graphics than ASCII art, whatever. Roguelikes or roguelites, whatever you'd like to call them. One of the earlier ones, and this was kind of latched onto, is like an indie genre. And one of the ones that kind of pushed this craze forward was The Binding of Isaac in 2011, which was heavily inspired also by kind of early Legend of Zelda games, and the structure of the dungeons basically is what they generated. And one of my personal favorites, Spelunky, is this dungeon crawler game, originally from 2008, and then they remade it for the Xbox and then kind of gave it a visual, like a facelift in 2012. But yeah, also like basically a platformer dungeon that, you know, works exactly like the genre leads people to expect. It gets more and more difficult as you go. And then in 2016, there was another one of these really ambitious, let's generate entire universes and entire planets with distinct terrain and flora and fauna and everything, called No Man's Sky in 2016. Which took advantage of, you know, some of the much more modern graphics techniques of the time. And yeah, there's probably a few others that you have thought of. Please send me or post to Piazza any of the examples that you know that I didn't list in this lecture. All right. So now we're going to get into some of the kind of the underlying theory of what procedural content generation is. And so we need to define something called the generative space. And the generative space is, simply speaking, is the set of all possible artifacts that your generator can produce. So you can kind of think of this part as like a button, sort of like press the button and it gives you a sample artifact. And that artifact may be randomly produced every time, but there's basically some way of defining what is the possibility space. What is the set of all of the, like what are the defining characteristics that you're choosing randomly from among? What are the ranges of numbers? What are the lookup tables? What are kind of what are all of the things that you have some choice in, some variability for, and how does that, and kind of those parameters define the space of possible artifacts. Now, you might not just have a button, you might have kind of an input where you also give the generator some constraints. And what that's going to do is shrink the generative space. It's going to say, okay, well, I had this ability to generate all these possible artifacts, but you fed in some constraints, and that led me to eliminate, all of the ones that were blue or something, right? Like that had some property. So you have these ways of constraining your generator to produce, usually you do this to create higher quality artifacts, or artifacts that sort of meet some criteria you have in mind. Okay, so to be a little bit less abstract, I really like this example from my colleague Mike Cook's blog post on generative spaces and possibility spaces, where he talks about Minecraft. So that's another example of games where you can use the Minecraft world generator. And he takes this example, which is just flat grass world with only grass and nothing in it. And while that is a world that it's sort of possible to talk about and define in Minecraft, it's not something that the Minecraft generator would actually create. So the generative space is sometimes a strict subset of the possibility space. Most PCG algorithms can be thought of as having basically two stages. One in which we are defining the possibility space, so we're kind of building up all of these parameters and axes of variation that we can use to create an artifact. And then a second stage, which is where we call our possibility space, we kind of winnow it down or refine it or constrain it to get a generative space, which is a strict subset. And the second set of methods is known as subtractive. It's kind of subtracting artifacts from the generative space. And the first is sometimes known as additive methods. So examples of some techniques that we're going to talk about in the course in general are directed randomness and grammars for additive techniques. And in the subtractive category, basically these are all methods of searching through the generative space or the possibility space and saying, like with evolutionary algorithms, you're kind of doing an iterative process with some randomness involved in order to search through that space for artifacts which meet a certain threshold of quality. And then things like constraint solvers and search-based methods are kind of strictly like yes or no, does this thing have the property or doesn't it? And if it does, then it's, then it's a member of the set. So you kind of are defining like characteristic functions for what the valid artifacts of the set would be. So today we're going to focus on an additive technique called directed randomness. And it's pretty much as simple as you could imagine for any kind of procedural content generation. Directed randomness is simply using randomness in the decision-making process while your generator is creating its stuff. So this actually gets to a point that I kind of glossed over earlier, is like, why do we consider procedural content generation to be AI in the first place? Well, if you remember at the very, very beginning of this class when we kind of talked about what AI even is, and especially in the context of games, you can kind of, reduce it in a way, or at least it's like one philosophy of thinking about artificial intelligence is that it's anything that's kind of trying to replicate something that a human would ordinarily be associated with doing, or considered better at doing than computers. So when it comes to design and creativity, generally, humans that's thought of as being a skill that humans kind of have in a more natural way than computers do. And so anytime that we're asking the computer to do this sort of creative task, we are sort of, one way of thinking about it is like simulating the human creative process. So that's why we kind of talk about this in the category of AI. And the idea of directed randomness actually kind of predates the digital and artificial intelligence sense of the word. So in this paper that I absolutely love from 2015, An Analog History of PCG, Gillian Smith actually uses this term, or I think she says directing randomness. And one of her example, or I guess in this paper, she's trying to kind of make connections and links between the techniques that we use for video games and in the digital space and things that artists have been doing in their creative practices sort of manually for much longer. So one example is like in generative art. For example, in 1951, an artist named Kenneth Martin created this piece called Chance and Order, where he simply randomly generated pairs of points on a grid and then drew lines connecting those pairs of points and rendered the result as a painting. So in the digital world, we need to, in the physical world, we can like roll dice or whatever, but in the digital world, we need to figure out how, we need to use random numbers. Most languages, of course, have built-in libraries for this, but it's worth knowing kind of what the properties of those are when you do use them. So in some cases, you might need true randomness, which is using some physical source of randomness, like radioactive decay or something. Then there's pseudo randomness, in which you provide a seed value, and with any given seed value, the sequence of numbers that's going to be created is the same for every seed. Now, a lot of pseudo random algorithms have the property that they're reversible, which means that given the sequence of numbers, you can reverse engineer what the seed value was. On the other hand, cryptographic randomness is similar to pseudorandomness, except it's specifically designed not to be reversible. So you can't determine what the seed value is given the sequence. Now, in PCG algorithms, we typically want pseudorandomness because, well, it has the nice property that if you keep track of your seed value, then the results are reproducible. So you can test your program with the same seed value every time and kind of see uniformly what changes between iterations. Or if you have a bug or something, then you can reproduce that bug by providing the same seed value. So for a pseudo-random number generator, you provide the seed from, like, after generating I numbers, and then it produces a new seed for kind of time step I+1 and a new random number. So it kind of keeps like cyclically feeding back into itself. As long as you start with the same seed, then it's going to generate the same sequence of next seeds and random numbers. So as an example, the game Elite, which we talked about at the beginning, uses pseudo-randomness. They had 8 galaxies, each with 256 planets, and they used the same random seed to generate all of the data for each of these galaxies, including the data for individual planets. So you can see each planet is associated with a location in the space, and so you can calculate how many light years away it is from where you currently are, an economy, a government, tech level, population, and so on. Now, some of these things are just numbers, which probably have specified ranges. You'll notice there are also some quality, some strings, like mainly agricultural or democracy, these strings just come from a lookup table. So you can associate the random seed with some number that you can map to the lookup table and get a string. And in some cases, you might be combining words from 2 different lookup tables. Like mainly maybe comes from one lookup table and agricultural comes from another one. So you can get different combinations. Now, this is a pretty simple form of using randomness in PCG. And of course, simple is good if you can get away with it, but you can't always get away with it. And some of the problems that this original approach to PCG had were that it just didn't have very high quality solutions. So some of the planets were too far away. It just didn't make sort of sense, it made the player experience more annoying. And in some cases, they were generating, yeah, so you can see the planet also has a name. This one is Ontamax. And that was just like, you know, like a somewhat randomized combination of letters and syllables. And some of those turned out to be profane. So, you know, unless you can kind of get a sense for what all of the different combinations are in your lexicon, then, you know, you might wind up having like artifacts in your PCG that are not what you wanted them to be. So that we can kind of classify the problems that this generator has is being under constrained, right? This generator is, well, it's a strictly additive generator. It's defined all of the possibilities, but we haven't given it any sort of criteria for quality. So it doesn't have any constraints or any way of kind of culling down the generative space to limit it to only those which have certain properties. Okay, so this gets us into our first generative technique that we're going to be talking about, which is object placement. So think about like the star fields in Elite, right? So you have stars scattered around various positions at different levels, or in other scenarios, maybe you have a map, your town map, and you've got different buildings that you want to place, or you've got an outdoor space with tufts of grass or trees that you want to put in the terrain. Basically, placing objects around in a two-dimensional or three-dimensional space is a pretty common task in PCG. So one approach to doing this is actually based on something called Halton sequences, which are, strictly speaking, not random or even pseudo-random as an approach. But the thing is, they kind of look, they look more reasonable for certain applications. So the square on the left here is strict randomness, and you can see how it kind of results in some places where things are sort of clumped together. So there's not, you know, it's because it's strictly random, it's, you know, there's not like even spacing between all of these different things. The Halton sequence, which is over here on the right, kind of creates more evenly spaced out artifacts. Okay, so how does that work? And then the other example I'm going to tell you about is Poisson disks. So Halton sequences don't necessarily guarantee that there's no overlap between all of your objects, and Poisson disks, so this again is an example of strictly random placement. Poisson disks assume you have some known radius for each of the objects you're placing, and you just want to make sure that they don't overlap with one another. Okay, so I'm going to stop share and switch over to the .chem now. So the idea behind Halton sequences is to pick two small coprime numbers, and so each number is associated with a sequence. So you can have Halton of some number b, b for base. So given some base b at index is going to generate a sequence of numbers. Let's say 1. All right, so you can think of this as also being indexed by, you know, by an index I to get x of I. Okay, so you can feed into this any, you know, small number, and so a common pair of coprime numbers that's used for Halton sequences is 2 and 3. And so you would call basically the Halton sequence generator on 2, and this is going to give you some sequence of fractions. And then the Halton sequence on 3 is going to give you some other sequence of fractions. You have x1, x2, x3, and so on, and then y1, y2, y3. And then to get your coordinates, so this is a pair of numbers because I'm assuming 2 dimensions. So you have to generate one sequence for every dimension that you're working in. If you're working in 3 dimensions, and this is a triple. So the coordinates that are generated are just the pairwise grouping together of these coordinates. So x1, y1, x2, y2, x3, y3, and so on. Okay, so how are these generated? And these are generated as coordinates on a, assuming a unit square. So if you have, 0 to 1 along each axis, then these are going to generate some fractional values that determine your coordinates in Cartesian space. Okay, so now let's talk about this sequence. So how do you actually generate the Halton value for a base and an index? Okay, well, we can kind of talk about it intuitively first. So let's suppose our base is 3. Then what we're going to do is we're going to divide the unit. We're going to divide 1 by this base. We're going to get 1/3, and then we're basically going to go up in increments of that value before we just up until before we get to 1. So we've got 1/3, and then we're going to increment that by 1/3, and we get 2/3, and doing it again would be 3/3. So that's 1. We skip that one. Okay, then the next iteration, we multiply this base by itself. Or we multiply the denominator by the base, rather. So the current denominator is 3. So now 9 is going to be our denominator, and then we start with 1/9, and then we keep going up in increments of 1/9. So we have 1/9, 2/9. We might have 3/9, but that's actually the same as 1/3, so we already have that one. So we don't include it. 4/9, 5/9, 6/9 is the same as 2/3, so 7/9, 8/9, and then 9/9 is 1. Okay, and then next we again multiply the denominator by the base. So then we go to 1/27, which is 3 cubed, and so on. Okay, so that's how we calculate it for the Halton sequence for a given base. And in general, this algorithm looks as follows. So we initialize our result value to 0 and our denominator to 1. And then while the index I is greater than 0, we are going to multiply the denominator by the base value, add something to our result, which is going to be the index mod the base divided by the denominator. So this is the fraction that we're creating. And then we're going to update our index to be the floor of itself divided by the base. And then finally, we're going to return that result. Okay, so pretty simple in terms of number of lines of code and so on. I'm going to go ahead and put a few minutes on the clock now for you to work this out for a base, to work out the Halton sequence for a base value of 2, and just work out the first, so you don't have to go through and apply the algorithm strictly, but you can, if you can kind of just think of it in this intuitive way, that's also fine. So if b equals 2, then what's the sequence going to be for the first, say, 10 numbers? So I'm going to put 5 minutes on the clock now. You can pause the video if you need more time than that, and then we'll check back in once that's done. All right, I'm gonna go ahead and stop it there. Feel free to pause the video if you do need a little more time. Okay, so hopefully what you should have come up with was sequence 1/2, 1/4, 3/4, 1/8, 3/8, 5/8, 7/8, and then 3/16, 1/16, and 3/16, 5/16, and so on. So yeah, so it's just skipping the fractions that are duplicates of ones that came previously in the sequence. Okay, so if we were trying to generate positions for two-dimensional object placement, we would simply then pair these up. We'd say this is the x-coordinate, this is the y-coordinate, and then scale that with whatever the dimensions of our actual grid are. Since these are just fractions, we'll place it 1/3 of the way up and 1/2 of the way over, for example. Okay, so that's how Halton sequences work. Next, I want to talk about this Poisson disk concept. So remember, so Poisson disks assume you have, so this is just like a way of generating points. If you have disks, then your disks have some radius value, r. Okay, and so at first, just to keep things simple, we'll assume that all of our disks have the same radius. So in order for them not to overlap, the centers have to be at least 2r apart, right? That's what it means for them to not be overlapping, but they could be, we provide some parameters, some constant value k, which is known as a packing density. And k is basically the max value apart that these disks can be. Accounting for their radii. So this is going to be 2r plus k. Okay, so now we have a range between which we can generate a random, basically a random separation from a given point representing the center of a disk. Right, so we have 2r as our minimum and 2r plus k as our maximum. Okay, so what we're going to do is maintain an active list of disks. Disks, I guess, with a K, and that's going to start out with one point. It can be a point in the center of your grid or a point that's randomly placed. And then the idea is that we're going to start kind of generating points outward from here, right? So we're going to start. Let me do this a little bit bigger, right? So if you generate some point kind of close to the center, then we're going to generate, some sequence of random angles and distances between 2r and 2r plus k away from our center, and then we're going to make those the center of some new disks that we're going to place. Okay, so this is our original disk, and then we've got some more disks that show up. Okay, and now this was our original active disk, and now we're going to add all of these to our active list of disks. And then on every iteration, we pick one of these active disks from our list and we recurse, right? So we say, given, so suppose we selected this one next, now this is our active disk, and we're going to start generating a sequence of disks some distance away from that. Okay, now every time we generate these disks, so this one, for example, is going to potentially create a disk that collides with, that overlaps with a previously existing disk. So we have to, every time we add a new disk, we basically have to check whether there is overlap with anything else that's been added to the list. And if so, then we discard that disk. We just simply don't add it. So once a disk is added, it always stays there. We're never deleting anything that we've added before, but we are making sure to be careful not to add any disk that overlaps with a previous disk. So I want to take a second to ask you to think about what the performance critical part of this algorithm is. So what's the part that's going to potentially take the most running time for us to do? Okay, and the answer is checking for overlap, right? Basically, for each of these disks that we consider adding, we have to go through our list of potentially our list of active disks and figure out whether it intersects with any of them, which is going to be its own calculation. So this is all if you do it naively. What we wind up doing in practice is implementing a grid system. So basically, we divide up our space into a grid, and this can be at the pixel level. It doesn't have to be a really coarse-grained grid, but we just divide our space up into a grid of locations, and then every disk that we place is going to occupy some number of those disks. So in this case, it occupies this one, this one, this one, this one, this one, this one, this one. So there are 9 grid positions that would now be considered occupied by this disk. So whenever you generate your disk, you have to calculate which of the grid positions it occupies, and then basically you just store a data structure, which is a 2D array of bools. Right, you store whether or not there's a disk already occupying that cell in the grid, and anytime you add a new one, you calculate the cells that it would overlap and simply look up in this array whether there's already some piece of some other disk there, which is just whether it's marked true as opposed to false, and if so, then you reject that disk. Okay, so that's how Poisson disks work. Now that remember I said this is assuming that all of the disks that you're placing have the same radius. Now suppose you had multiple like variable radii. Your disk could have any of a number of different radii. But at any given point, you basically have pairwise, you're only considering one active disk at a time. So anytime you're adding a new disk, you've only got 2 radii to consider, R1 and R2. So now the simple kind of generalization of this algorithm is that instead of 2R plus K, you have R1 plus R2 plus K. And so then you can accommodate disks of various sizes. Okay. To stop sharing. Go back to sharing. Right, that's why that was confusing. Okay. So going back to slides. All right, so those are a couple of the techniques. So the book goes into some more details and variations on these things. For object placement, it talks about radial object placement, like placing petals around a flower and how you do that in a natural looking way. But those are the 2 object placement algorithms we're going to talk about today. And now we're going to get into a little bit of dungeon and maze generation. So the problem here is similarly where, similar in the sense that we're kind of thinking about placing structures in 2D or 3D space, generally 2D, and it's fairly easy to generalize to 3 dimensions. So we want to kind of fill our space with random looking, with some amount of variability, but connected and navigable spaces. So now rather than placing objects, which might represent just sort of visual artifacts in the world, this is actually going to be the structure that the player moves around in. And this might be something, kind of that looks more like a traditional maze where your world is mostly made of corridors, or you might have some prefabricated elements like specific rooms that you want to include in your dungeon, and then just link them together kind of by randomly generated connections. So the techniques we'll be talking about include depth first backtracking, which is the kind of simple way to generate mazes of corridors that look kind of like this. It's your sort of typical labyrinthine sort of maze. We're going to talk about the minimum spanning tree algorithm and then recursive subdivision. Oh, I lost Zoom. I can't find my dot cam. Oh no. Okay, stop share. All right, there we go. Okay. Right. So maze generation. All right. The simple corridor construction versions of this all kind of, so they all assume that you have a regular grid structure. So I'm just going to kind of sketch this out. And the nice thing about the depth first backtracking algorithm is that it's actually easy to implement by hand. So you can kind of, I find it actually kind of meditative to sort of like pick a start, like maybe the top left corner, and then basically start doing this random decision making process. So the way this works is because we assume we have a grid, we have a strict like a finite set of neighbors. Sorry, I'm covering up the maze. We have a finite set of neighbors for any given cell that we can potentially move to. So we can start it anywhere on the grid, but assuming we start up here in this top left corner, there's basically 2 directions we can move, east or south. And we can pick one of those. And now we're in the cell and we can move south or east. Over here, we can move back west or east or south, right? So we can just kind of keep making these random decisions until we get to a point where there are no more unoccupied neighbors for us to visit. Okay, and then at that point, we backtrack just to the most recent point at which we had a choice, and we make a different choice. down to my next dead end, and so I backtrack back to here and keep going. All right, and then backtrack all the way back to here. It's the last place I had a choice, and keep going. Way back to here. And then eventually I've covered the entire space. Right, so that's a simple algorithm you can execute by hand. How does it look in code? We're going to start out with a set of locations. And it's initialized to just contain the start position. And then as long as that list is not empty, we are going to get the first value from it. Using inconsistent assignment notation here. Okay, so we're going to assign the first value of our locations to OCS, and then our next value is going to be some random unconnected neighbor, assuming it exists. Well, not assuming, but rather if it exists, then next will get assigned to a random unconnected neighbor of our current node. And then we check whether that in fact exists. So if next, then we go ahead and continue by pushing that next value onto our stack of locations. So this data structure here, we're assuming is a stack. So we're just going to push our next value and then continue when we do the next iteration through the loop. Now this very last value that we pushed is going to be at the top, and we're going to work on that next. Okay, so that's the idea. Just like keep going until you can't. Okay, so then the you can't part is in the else branch, and in that case, you just pop the location stack. So you just pop off that that location because there's nothing else you can do there, and the next iteration through the loop, you'll check the previous one you visited, and if that doesn't have any neighbors, you'll keep going. You know, basically each iteration will continue going backwards until you get to one that does have some random unconnected neighbor that you can traverse. Eventually, the whole locations list will be empty, and then at that point, you will have covered all of the cells in your grid. Okay. So that's the depth first backtracking algorithm. And there's an alternative to depth first backtracking algorithm, which I'm not going to get into too much, but because you've probably seen it in other classes, I would expect. So minimum spanning tree, or MST algorithms, operate on weighted graphs. Generally, you assume that they're undirected. So you have basically some set of nodes that are connected to each other in various ways. And there's probably lots of like multiple connections between things because these edges are going to represent all of the possible connections. So if this were a grid, right, it would look, the connections between the edges would just look like a grid shape, where each node is a cell of the grid. But the difference is now you can label these edges with weights. So you can say, you can basically assign a cost to including them in your graph. You can say, some of them have very low cost, some of them have very high cost, and the kind of relative costs of these edges will determine how the minimum spanning tree algorithm works. So a minimum spanning tree algorithm, the goal is to create a subset of the nodes in the graph that visits and that connects, rather, all of the nodes in the graph, right? So we want to be able to visit all of the nodes in the graph, but we only want a subset of the edges, and we don't want any cyclical connections. So, for example, like this would be an example of a spanning tree. I include this middle edge and all of the radial edges coming out from it, and if yeah, so all of the ones that have kind of bolded in this graph, it's a spanning tree because it covers all the nodes, and it's a tree, right? Not a graph with cycles in it, because we've excluded the edges that would create those cycles. And so the minimum part of minimum spanning tree basically just guarantees that the sum of edge weights on all the edges that are included in the tree is as small as it can possibly be. So basically this gives you more authorial control in your generator, allows you to express more constraints in terms of saying which connections in your grid or your set of locations in your game you want to prioritize connecting versus those that you only want to connect in maybe very rare circumstances. Okay, so there's two common algorithms for doing minimum spanning trees, prims and Procedural. And prims is covered in the textbook. It's also one of, these are both very like easy to look up kinds of algorithms. I expect that you've probably also seen them before in some of your classes, so I'm not going to go into too much detail. Prims is pretty simple. Basically, prims is the one that says you just keep a list of unvisited nodes, you initialize it with all of the nodes in your graph, and then you find the lowest cost, the node that you can, that's unvisited, that's the lowest cost to get to, and then add that to your, add the edge that connects that node to your graph, to the tree. And then just keep going until you've visited every node. Okay, so these are basically both algorithms that can generate random connections between grids or graphs of nodes. And what these two algorithms kind of assume, or like I would say, maybe they blur the distinction between rooms and corridors. Or rather, they don't really have a notion of rooms, right? This is all kind of like, these are strictly just like corridors. Like you could think of these as narrow hallways that your player is wandering through, but there are no like, the sort of spatial dimensions of the places that you're connecting are not represented in these algorithms. So the next example of a technique I'm gonna tell you about is called recursive subdivision. And this is one that actually generates rooms and corridors. So, so by a room, I mean something that can have variable size, maybe variable shape, and then corridors are, simply like the thin sort of connecting areas between rooms. And you can also potentially join corridors together. I mean, that's what we were doing in the maze examples. Like every connection was a corridor connecting to a corridor. But here we have corridors connecting rooms and corridors coming off of corridors as well. Okay, so we're calling this thing a room and this thing a corridor. Okay, so in recursive subdivision, it's basically exactly like it sounds. We're going to start with our overall space, and we're going to start basically cutting it in half. So we're going to say pick some randomized value for where to draw this line, maybe here. And then these are our subdivided components, and we'll label them A and B. Okay, and when we pick this line, we want to be sure that basically, so you've got some like here, maybe L1, L2, and you want to be sure that the ratio of L2 to L1 is somewhat reasonable, right? That these are like similar sizes. You don't want to generate, you don't want to like subdivide and have a really narrow room up here. Maybe you have some restrictions also about the width versus the height of your subdivided compartments. So you have some criteria that determines what a valid subdivision is. And whenever you generate your subdivision, you check whether it satisfies that criteria. If not, then you do it again. Right, is one way to do it. You could also restrict it to be in a certain range. But basically, you have some kind of quality criteria in terms of the size and shape of the subdivisions you're creating. So you create your subdivision. Maybe you do it horizontally first, and then in the next iterations for the subcomponents of that map, you're then going to draw a vertical line and basically do the same thing. So now we're going to do some vertical subdivision, and for A, so A now refers to both of these components, B refers to both of these components. We're going to label each individual one, so it's going to be C, D, and E, F. Okay, and then maybe we do one more layer of subdivision, and we say each of C and D. We go back to the horizontal subdivision. Each of C and D can divide like this, and this becomes G, H, I, J. Okay, so this recursive scheme for subdividing the space, you can see it kind of has a tree structure to it. So we started out with our root node, and then which represented our whole space, and then we divided that into A and B, and then we divided A rather into C and D, and B into E and F, and further subdivided C into G and H, and D into I and J. Okay, so this gives us our subdivision. This gives us basically all of the shapes that we're going to make our dungeon out of, and I'm going to kind of redraw them, but slightly separated from each other now. Imagine taking a pair of scissors and doing this. Okay, and I'm going to label it with basically the leaf node of the tree that it represents. So this one is going to be GH, this one's going to be IJ, this one's going to be EF. So each of the rooms corresponds to a leaf of the tree. And the internal nodes, so C, D, A, and B, are now going to correspond to corridors. So so there's a corridor between two rooms if they share a parent. So G and H, we're going to have a corridor behind them, and we're going to label that with C. So C represents the corridor. I and J have a corridor, which we represent as D. E and F have a corridor, which we label with E. Okay, and then at the next level up, now we've got internal nodes that we want to join. So C and D also share the parent called A. So we want to connect C and D with a corridor. Now we're connecting corridors with corridors and label it with A. We can then see that A and B should also be joined by a corridor, and that's just the root node of the tree. So this gives us sort of a system of rooms and corridors using a simple recursive subdivision technique to generate the connections between them. Now, you don't have to strictly connect corridors to corridors at the node levels of the trees. You can also connect like any room in the subtree to any other room in the other subtree. So instead of connecting like the C and D corridors with the corridor A, I could have connected like the room G to the room J, or to the room I, right? Anything from over here connected to anything from over here would also be a reasonable way to do that. Okay, so that's how recursive subdivision works. And that is the end of the technical content of this lecture. I wanted to also point you at one of my favorite examples of analog procedural content generation. So if you like Dungeons and Dragons, but your favorite part is like being a DM and coming up with the worlds and like the setting that your characters get to explore, this is a single player game for you. So this is a PDF that you can buy for $5 called How to Host a Dungeon, How to Host a Dungeon. And it is basically just a sequence of instructions that you can follow with some pens and paper and dice and tokens and maybe some board time at home that you would like to spend alone instead of with your younger siblings or whatnot. Yeah, so this is a fun kind of activity that you can do. I'm thinking about posting some extra credit on Piazza if you do this and post a picture of what you came up with. So it's basically just you roll dice and then use the result of the dice using these lookup tables to figure out what your steps are. So it starts out by like defining these different strata of your dungeon, and then you pick a layer of your dungeon, and you start filling it with things based on the outcomes of the roll of your die. And it goes through several different like eras of time, including kind of like the generation of the terrain and the like pre-civilization kind of changes to the world, and then gradually introduces characters like elves and gnomes and various fantasy world things that are going to change like the lore and the story that kind of builds up around this location. So that's How to Host a Dungeon. If you are interested in this topic of sort of world and terrain generation more generally, there's two really great talks I recommend. One of them is from the Strange Loop Conference in 2018, Mouse Reeve. It's called Mapping Imaginary Cities. And the other one is Kendra, who's a programmer at the company who made No Man's Sky, talking about how they do their planet generation at GDC 2017. So definitely check those out if this topic interests you. And with that, I will point you at the link to today's quiz. And hopefully with the material that I covered today, you should be able to answer those questions. That's it for today, and I'll see you next time.